Hi. Okay, let's talk about all of those flavor anomalies. In recent years, there have been a number of experimental results in particle physics that have shown small but unexpected deviations from the predictions of the standard model. These results have been measurements of observables related to something called flavor. Some of those observables are listed at right, but there are also more. None of these discrepancies with the standard model prediction has reached the 5 sigma threshold that particle physicists usually require in order to declare discovery of new physics. But there are a bunch of these results. And, intriguingly, it's possible we're starting to see a pattern in these deviations from the standard model predictions. Because of the number of these results, there is starting to be serious speculation that we're seeing tentative signs of new undiscovered physics beyond the standard model. Okay, so let's talk about them. There are 3 sets of these experimental results that we've already covered on this channel. First, there's muon G-2. If you're interested in that, you might want to check out the playlist Miniseries on G-2 of the muon. Next, there's RK and RK star. You can find out about these in the video called New Flavor Physics in LHCb Data. And thirdly, there's RD and RD star. If you want more info on that, check out the video entitled New Physics Involving the Tau Lepton. We will briefly be reviewing these here, but we will leave out most of the details. Okay, those are the most famous anomalies, but there are more. So we'll talk about the less well-known ones too. There's a lot to cover, so I should note that this video is going to be a bird's eye view only. We will be leaving out almost all of the experimental details. You should also know up front that we'll be quantifying these observed deviations from the standard model predictions in terms of sigmas. If you'd like more information on what these mean, please check out the Understanding 5 Sigma playlist. Otherwise, it's good to be aware that particle physicists rarely declare discovery of new physics unless they have an observation that disagrees with the standard model prediction by at least 5 sigma, and sometimes when there's a discrepancy of at least 3 sigma, people will start throwing around the word evidence. Up front, I'll list a useful reference from Altmannshofer and Stangl. I won't be presenting any of their results, but I did use their paper as a guide in putting together this video. References for muon G-2, RK and RK star, and RD and RD star are given in the previous videos, so I won't repeat them here. For the other experimental results, references will be given throughout the video and in the description below. Okay, let's very briefly review flavor in the standard model. In the standard model, there are 6 quarks and 6 leptons. In this video, we'll be especially paying attention to processes involving the B quark, the S quark, and the muon. The quarks and leptons have interactions which are mediated by the gauge bosons, which are the photon, the Z, the W+ and W-, and the gluons. And also, there's the Higgs boson. Now, the quarks and leptons are arranged into 3 families. These families are identical, except for mass terms. If we find that the 3 families don't all interact in the same way, except in ways explainable by mass terms, then that's a sign of physics beyond the standard model. Now, flavor just refers to the identity of a particular quark or lepton. So if a particular flavor of quark or lepton acts differently than we expect, that's interesting. Okay, Let's start by very briefly reviewing the results we've seen before on this channel. Muon G-2, RK and RK star, and RD and RD star. First, G-2 of the muon. Muon G-2 is related to how the muon interacts with the photon. It was recently measured by the Fermilab Muon G-2 experiment. Getting the standard model prediction for Muon G-2 is not a trivial task. To get it to the precision necessary to compare with experiment requires calculating thousands of Feynman diagrams. Muon G-2 is interesting because there are lots of scenarios of new physics which could cause its measured value to differ from the standard model prediction. Both the measured value and the standard model prediction are very precisely known. Currently, the combined experimental result from Fermilab and Brookhaven National Lab differs from the standard model prediction by 4.2 sigma. Okay, so that was Muon G-2. Now let's move on to RK and RK star. RK and RK star involve looking at decays of particles called B mesons. Mesons consist of a quark and an antiquark. Let's look at a meson called a B+. A B+ consists of a B antiquark and a U quark. It can decay to a lepton pair and a meson called a K+, which consists of an S antiquark and a U quark. So the B antiquark in the B+ turns into an S antiquark and emits a lepton pair, which here is either an electron-positron pair or a muon-antimuon pair. The interesting question is how often a muon-antimuon pair comes out relative to an electron-positron pair. In the standard model, electrons and muons have the same interactions, so the ratio of these two processes should be very close to 1. And this ratio, up to some experimental complications, is what we call RK. RK star is the same thing, but uses a neutral B0 meson and a neutral K star meson. In the standard model, both RK and RK star are very close to 1. These were recently measured by LHCb. There's one result for RK and 2 for RK star. All 3 are lower than expected, with significances ranging from just over 2 sigma to just over 3 sigma. So there's a hint that the muon to electron ratio is lower than what the standard model predicts. Okay, now let's look at RD and RD star. These are also measured looking at decays of B mesons. These measurements are hinting at a difference between the tau lepton and the electron and muon. Again, we have a B meson, which consists of a B antiquark and some other type of quark. This can decay to a D meson, which contains a C antiquark, and a charged lepton and a neutrino. The charged lepton can be an E+, a positron, a mu+, or a tau+. The underlying process is that the B antiquark in the B meson can turn into a C antiquark, emitting the charged lepton and neutrino. The other quark in the B meson, denoted here as a Q, just goes along for the ride and ends up in the D meson. RD looks at the ratio of the rate of decays containing tau leptons to the average of the rates of decays containing electrons and muons. And RD star is the same, except it uses a D star meson, which is like a D, but a bit heavier. The standard model predictions for RD and RD star are actually rather different from 1, because the tau is much heavier than the muon and electron. Here are the standard model predictions, in case you're interested. The heavy flavor averaging group averages the measurements from the Babar, Bell, and LHCb experiments. When they combine the results for RD and RD star, they find that the observed value is about 3.1 sigma higher than the standard model expectation. So there are more taus than expected relative to the numbers of muons and electrons. Okay, now that we've reviewed those measurements, let's go on to the others. We'll start with the branching ratio of B to K or K star and a muon-antimuon pair. A branching ratio is just the fraction of the time that the particle decays to that particular set of final state particles. So here we're talking about the fraction of the time a B meson decays to a K or K star and a muon-antimuon pair. Let's think back again to RK and RK star, which we've already seen. There we looked at a B decaying to a K or K star meson and a lepton pair. The interesting question was the ratio of decays containing a muon-antimuon pair to those containing an electron-positron pair. The ratio was smaller than expected. LHCb has also published measurements of the branching ratios of B mesons to K or K star mesons and a muon-antimuon pair. They look at this process as a function of Q squared, where Q squared is the invariant mass of the muon-antimuon pair. These show fewer decays to mu plus mu minus than expected. So it's not just that the ratio of muons to electrons is low, but also that the rate of decays containing muons is itself lower than expected. Here are the references from LHCb. And here are their results. They measure the branching fractions of the processes involving muons. They find 3 that are between 1.7 sigma and 2.2 sigma low. There is also a fourth measurement. It is in agreement with the standard model, but slightly below it. But we see that all of these results are lower than the standard model predicts, so there are fewer decays with muons than expected. Okay. Next, let's look briefly at angular variables in the decays of B mesons to a K star and a muon-antimuon pair. So there is more that can be measured in the decay B goes to K star mu plus mu minus than just its rate. Here are the references for what we're talking about next. Okay, so LHCb looks at the decay B plus goes to K star plus and a mu plus mu minus pair. They also look at the decay with a neutral B meson and a neutral K star. In both decays, the K star will decay. LHCb looks at functions related to the angles at which the final state particles are emitted. And these functions show some deviations from the standard model prediction. Now, quantifying this disagreement depends on some assumptions. We'll briefly come back to this at the end of the video. Okay. Next, let's look at the branching ratio of a B sub S meson to a phi meson and a muon-antimuon pair. To understand this process, let's go back, yet again, to the process where a B meson decays to a K or K star and a mu plus mu minus pair. Here we've pictured the case involving a B plus and a K plus. This decay is brought about by the process where a B antiquark decays to an S antiquark and a muon antimuon pair. The B plus also contains a U quark, but it just goes along for the ride and ends up in the K plus meson. Let's imagine what happens if that U quark is replaced with an S quark. Okay, so we replaced that U quark with an S quark. Now the original B meson contains a B antiquark and an S quark. This is called a B sub S meson. The meson it decays to contains an S antiquark and an S quark. This is a phi meson. But the quark level decay is the same as what we looked at earlier. So LHCb measures this branching ratio of a B sub S to a phi and a muon antimuon pair. Here's the reference. In the region where the standard model prediction is the most precise, they find the observed differential branching ratio to be 3.6 sigma lower than the standard model prediction. So yet again, we're seeing a process with muons occur at a rate lower than that expected. Okay, and finally, let's look at the branching ratio of a B sub S to a muon antimuon pair. To do this, let's look again at the B sub S meson that contains a B antiquark and an S quark. Okay, before we looked at the process where a B antiquark decays to an S antiquark and a muon antimuon pair. In particle physics, this implies that we would also have the process where a B antiquark and an S quark can annihilate into a muon antimuon pair. This can give the decay B sub S goes to muon antimuon. This branching ratio of the B sub S meson has been measured by the LHCb, ATLAS, and CMS experiments. These results have been combined. If you're interested, you can take a look at this reference and the references cited therein. Each experiment's result was compatible with the standard model, but slightly low. When they are combined, the result is 2.4 sigma lower than expected in the standard model. So again, we're seeing a lower rate than expected. Since then, LHCb has updated their results. Their new result has moved a bit closer to the standard model prediction, so a new combination would probably show a slightly less significant deviation than what has been reported so far. Okay, so let's look at the big picture. Well, we don't really know the big picture yet, so let's instead look at a possible big picture. Actually, that's probably still too ambitious. Let's try a possible medium-sized picture. So far, we've seen deviations from the standard model predictions in a whole lot of measurements. In this table, I've put in signs to show whether the observed result is higher or lower than the prediction. Is there anything tying these things together? Well, first of all of these processes involve muons. And all of them except muon G-2 and RD and RD star are directly related to a process involving a B quark, an S quark, or their antiquarks, and a muon antimuon pair. Two of those are deviations seen in angular distributions. But all the rest are measurements indicating that processes involving B quarks, S quarks, and a muon antimuon pair happen less often than the standard model predicts. So we have many hints that processes involving a B quark, an S quark, and mu plus, mu minus occur less frequently than expected. We could imagine writing down interactions from physics beyond the standard model, which would cause this effect. It has been pointed out that if you do, it is possible to find such interactions which also make those angular distributions make a bit more sense. So it's possible that those measurements are also hinting at the same new physics. Tackling all of these processes along with muon G-2 and RD star would be a bit more involved, and that's beyond the scope of this video. So it's possible that we're seeing tentative signs of physics beyond the standard model. It's also possible that we're not. But even if it is new physics, there is currently no smoking gun that can definitively tell us what new physics we're seeing. All of these results need to be understood in the context of loads and loads of other observations, including those which agree with the standard model. Time and future results will resolve the issue.